Now we're going to introduce a useful discrete joint distribution called the multinomial distribution. And this is actually a natural generalization of the binomial distribution. So where does this arise? These types of probabilities are going to arise anytime we're sampling at random with replacement a fixed number of times from a categorical distribution. For today's examples, I'm going to do simple things like dice or marbles. But in reality, this situation where we're modeling this sampling with replacement from a categorical distribution actually shows up quite frequently in real-world scenarios. And so we're going to see some more useful applications of this other than just dice and marbles in our future lessons. But for today, while I'm introducing the concept, I'm going to stick with these more concrete examples. So, for example, if I have a bag of marbles, 60% are blue, 40% are not blue, and I want to go sample, say I sampled 10 marbles out of here, I can then ask, what's the probability that I see 5 blue and 5 not blue, or 3 blue and 7 not blue? That is directly asking me to model a binomial distribution. So the extension of this is when I add more than just two categories, or I have more than just two categories. And this now becomes a multinomial distribution. Again, the goal is going to be to count the number of each category that ends up in our sample. So if we remind ourselves of the PMF for the binomial random variable, we see that it depends on one parameter, P, which is my probability of what we're considering a success. And I then say, okay, I have probability of success is this. I have K successes and minus K failures. And then I need this binomial coefficient to think of all the possible ways that I could order exactly K successes out of N trials. Well, now we're going to have the same idea, but we're going to need to generalize. I'm going to have to generalize this binomial coefficient and then generalize this term here. So let's try it with an example. We're going back to that same bag of marbles. 60% are blue, 30% are green, 10% are red. Suppose you do a random sample with replacement of, and again, what this means with replacement means I draw a marble out, I look at its color, I record it, then I put it back in. Draw a new marble out, look at its color, record it, put it back in. Okay. So that with replacement really means that if I think of these as random variables, they're independent of one another. If I think of each of my draws as a random variable, then whether I get a blue on the first draw versus the second draw versus the third draw, those are all independent of one another. And they're all identically distributed based on this given distribution. Okay, so what's the probability of getting this sample? So probability of blue, green, blue, 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 green, red versus what's the probability in general of getting 4 blue, 2 green, and 1 red? So these are different questions. The first one has a very specific order, and the second one is allowing for any combination, any particular order, as long as I have those exact counts. All right, so let's do the first one. I can use the product rule because these are all independent of one another. And so the probability of this joint situation happening is going to be the product of the individual probabilities like this. And so that's what I have here. Now, when I want to think about the probability of 4 blue, 2 green, 1 red, I again have to think of all the possible ways that I could order these 7 draws so that I get that exact distribution. And in particular, let's look at the first piece because that count is going to be the number of ways that I can reorder these. And then this second part is just the probability for each of those ways. So this looks very similar to what we were doing with the binomial distribution. So what does this mean and why do I have this here? So first of all, altogether, this is the probability. It's called a multinomial probability. And notice I am using both the addition and the multiplication rule because I'm saying for a particular outcome, say what I had in Q1, here's the probability of this ordered series. And I did that using the multiplication rule. And then the addition rule comes in because I now need to add up the number of ways. So where is this 7 factorial and then the denominator coming from? The 7 factorial is from the fact that I have 7 items here. So let's forget that we have some repeats first. Just imagine, we'll just call it like item 1, item 2, item 3. So I'll call it like x1, x2, all the way up to x sub 7. So if I want to think of the number of different orderings that I could do with that, where order matters, there's going to be 7 factorial because I have 7 choices for the first, 6 choices for the second, right? And so that's going to give me that number of possible different permutations. But that's not taking into account the fact of repeats. So when I have, for example, these 4 B's, I don't want to count, let's say that x1 was B, and let's call x3, x4, and x5, those are all B's. I don't want to count this ordering as different than if I were to write, let's say, x3, and then x2, and then x1, and x5, x4, and then x6, x7. So what you're noticing here is that these 3 here are still all B's. This one is a B as well. This calculation is actually counting those as different. And that means it's double counting things. It's double counting all the possible ways that I can rearrange those 4 B's. And if we think of that, I can rearrange those 4 B's, 4 factorial different permutations. So I have to divide that out. Same thing with those 2 greens. I can rearrange those 2 factorial different ways, and then the 1 red is just there. So that's what this is doing. And it's really the exact generalization of the binomial coefficient. So let's define it now officially. What's nice about the multinomial random variable is that to define the joint probability mass function, I don't have to use a joint probability table. I have a nice closed form function to describe the probabilities for any possible combinations. And so we can see here, this is what's generalizing from what I did on the previous page. If I want the joint probability for these different exact values, then I can take my multinomial coefficient here, and then I multiply by this. Now, what are all these p sub 1s versus p sub 2s? Again, that's just representing I'm allowed to have different probabilities for the different outcomes. So I had a different probability of a blue marble than I did for a red marble. Altogether, those probabilities have to add up to 1 because they have to account for every possible outcome, and they're going to be mutually exclusive. All right, so this is my closed form function for the joint PMF. And so that's just pointing out here that the probabilities of all the possible different like red, blue, green marbles have to add up to 1. And this C, again, that's saying the different possible combinations or the different possible numbers that I could get. 4 blues, 3 reds, 2 greens has to add up to N, the total number of draws I'm doing at the end of the day. The multinomial coefficient, I'm just writing it here again in terms of its generalization. This is how this notation exactly means to do this. Great examples in terms of dice or marbles, like this is where you'll see this, rolling 2 2s, 3 3s, 5 5s on 10 rolls of a fair-sided die. This one's a little more interesting, right? Is what if I want to generate a random 5-word phrase? What's the probability of getting 1 the, 2 bacons, 1 put, 1 on? So this gets a little more interesting when we start thinking about using this idea to analyze text. Now, these do have parameters just like the binomial had parameters. Now it has n, and then it's going to have these multiple p probabilities here, which is an p sub I is a probability of outcome I on a single trial. Where do we get these from? We can do this either by knowing ahead of time how many marbles are in there of different types, or we can just count up, especially if we were like analyzing a text document. I wanted to know the probability of seeing a certain word. I could just look through the entire text to count up how many times that word occurred out of all possible words in the text. All right, so let's do again a basic example just with fair six-sided die. What is this probability? Go ahead, put it on pause, see what you can get. So if you said this, you are correct. This one was obviously not as interesting because no matter what, I was always going to get 1/6 to the number of rolls because they were fair six-sided. If I had given you some different probabilities, it'd be a little bit more interesting here. In this case, my multinomial coefficient is this term, which ends up being 7 factorial divided by each of these factorials to account for the overcounting we're doing when we have repeats, right, in one of our draws. So at the end of the day, that gives you 420 times 1/6 to the 7th. Now we can simulate multinomial probabilities in Python, and this will be very useful in some of your upcoming assignments. So if I tell you in advance that you have a bag with 60% of marbles are blue, 30% are green, 10% are red, you're going to sample 7 of these, then I can use the built-in function mp.random.multinomial. The arguments are the n parameter here, so the number of trials, and then the specific probabilities of the different outcomes. And then what's going to come out is a count. So here, this is going to be, for example, the number of blue, because I gave blue first, and then I gave green second, and I gave red. So in a random sample from a multinomial with these probabilities, I ended up with 3 blue and 4 green and 0 red. But then if I do it again, right, I'm going to get a different outcome. So in this case, I had 4 blue and 2 green and 1 red. So that's the built-in function here, and that's going to be useful as we try to simulate these distributions. And that brings us to the end of our intro to multinomial probabilities.